Okay, so the idea here is I've got a revision tracker, P2, topic 5. Now I've not had any preparation, no scripts. I'm just going to try and cover quite a lot of topic 5 in about 5 minutes or so, just as a quick last minute revision thing for those of you who are getting ready for the P2 exams. So, describe the structure of nuclei of isotopes using the... Right, let's just start off with the atom. So the atom is made up of a nucleus, and the nucleus contains different particles, neutrons and protons. And normally in smaller atoms there's a fairly equal number of neutrons and protons, and then going around the outside in different energy shells we've got electrons, and the number of electrons is in an atom equal to the number of protons, so that the charges balance, so there's no overall charge. So an atom has got no overall charge because the numbers of protons and electrons are equal, but an ion has got a charge because the atom has lost or gained electrons, and that is very useful for your chemistry as well. But what we're interested in here really is nuclear physics, and so we're more interested in what's happening down here in the nucleus. So the nucleus is the part of the atom that contains the protons and neutrons. It's where all the mass of the atom is. And what can happen is if you pick an element, let's pick an element X, mystery element X, and we've got two numbers here in the periodic table that describe. Now the top number will describe the mass. It's called the mass number of the atom, and this one here is called the proton number or the atomic number. So the mass number is the mass of the atom. That tells us how many particles are in the nucleus, and the proton number is the number of protons in the nucleus. Now what can happen is if the proton number gets quite big, quite high, certainly in the region of the 80s, so 82, 83, 84, you end up with altogether in here almost 200 particles, and what can happen is that they get quite unstable. The forces that are holding them together in quite a big nucleus become unstable, and so what happens is this larger element, which has got quite a few protons, more than 82, 83, 84, has got quite an unstable nucleus, and this unstable nucleus needs to make itself more stable. It can't stay as it is. So there's a few different things that can happen to help it do that. I'm going to start with the first thing, which is just a little bit of energy can come out. So we got energy can come out of the nucleus in the form of a gamma wave, and gamma is a high frequency electromagnetic wave. So it travels at the speed of light. It's got no mass, it's got no charge. It can go through pretty much anything apart from thick sheets of lead or gold or several meters of concrete. And once the atom has got rid of some energy, it's a bit more stable. However, it doesn't affect the overall structure of the nucleus, and so the mass number and the proton number are unchanged. However, what can also happen is that we get this thing called beta particle. Now this is a strange thing. It's just an electron, which isn't in itself strange, but the beta particle actually comes from inside the nucleus, and there's no electrons here. So how does it happen? Well, actually what happens is that one of the neutrons inside the nucleus can decay and turn into, quite by magic, it turns into a proton plus an electron. Now this proton stays inside the nucleus, and then the ratio of protons and neutrons is more equal, and so the balance is better and the atom becomes more stable. In fact, when this happens, the proton number goes up by 1, and this element changes into another element. It actually becomes another element, but the mass number remains unchanged as well. All that is lost from the nucleus is 1 electron that shoots out from the nucleus, and we call that a beta particle. Finally, the third thing that can happen is an alpha particle can come out, and the alpha particle is made of 2 neutrons and 2 protons, and that's got a mass of 4. And this alpha particle, what it can do is it can shoot out and it might hit another atom out here somewhere, so it gets stopped quite easily. Its overall mass is 4. It carries a welcome to part 2 of P2 topic 5. I'm sorry, but I was interrupted halfway through the first one, but the lighting wasn't brilliant, so I'm hoping now that you can see this diagram a little bit better. And I think we just got to the alpha particle, saying it had been made from 2 neutrons and 2 protons, and it's got a double positive charge. When the alpha particle leaves the nucleus, it actually reduces the mass number by 4 because it's got 4 particles here, and the proton number goes down by 2. So again, this element turns into something else and becomes more stable. Now let's pick an example of an element that is particularly unstable. We've got uranium, which is 92, a very large atom, and if we pick a particular isotope of uranium, an isotope is an element. There might be various versions of this uranium. There might be uranium-238, uranium-235. They've all got slightly different numbers of neutrons. So this particular type of uranium is uranium-235. You might see it written like that, or you might see it written like uranium-235, just with the mass number. We know because it's uranium, it's got 92 protons. Well, this uranium is unstable, and it can split, into 2 daughter atoms, and we might get, for instance, krypton or xenon coming out as the products of that split. And this atom splitting has got a special name. It's called fission. Now we can actually make this happen. This uranium atom is teetering on the edge. It's just about, it could decay at any moment of its own accord, randomly. But if we take a neutron and fire it inside the nucleus of this uranium, what can happen then is that it will definitely split. And as well as making these 2 daughter atoms, which are smaller and therefore probably more stable, it also gives out 3 neutrons. 1, 2, 3. And lots of energy. We can harness that energy in nuclear power. The problem is we can also harness that energy in nuclear bombs, because what happens here is we've got 1 neutron going into this cycle and 3 neutrons coming out, and these neutrons are going to be knocking into other uranium atoms. You don't just get 1 uranium atom stood by itself in the middle of nowhere. This uranium atom will be part of a big lump of uranium, so all around it are other uranium atoms, and these are going to hit into it, and what they're going to do, they're going to make these other uranium atoms split, releasing energy. And then they will also release 3 neutrons, and again, so we end up with an avalanche. We start out with 1 splitting, then 3 splitting, then 9, 27, 83, 234. Before you know it, there's loads of energy. This is called a chain reaction, and the amount of energy just avalanches, goes off the scale. You have a massive explosion, and kaboom, that's the nuclear. Uranium is split, and we cause a chain reaction to happen. The energy flies out, loads of it immediately, in the blink of an eye, which could millions of times more energy. This is a nuclear reaction. This is a nuclear bomb, millions of times more powerful. Heavily, we have actually been able to harness that. If we can catch a couple of these neutrons, then we start with 1. We end with 1, and we get energy as well. So instead of a chain reaction, we have a steady reaction that we can control. And we can control that reaction by using rods called control rods. And we put them next to fuel rods made of uranium. And when the uranium kicks out all these neutrons, the control rods might be able to catch some of the neutrons. And then this 1 neutron goes on to keep the reaction steady. And so in a nuclear reactor, what we have is a collection of fuel rods and control rods, and what we do is, let's see, these are the fuel rods, uranium, 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 and these are the control rods. They might be just made out of something like boron, which is able to absorb neutrons. It can absorb the extra neutrons and yet sustain the nuclear reaction, so it's constantly giving out energy at a steady rate. We can adjust, very carefully adjust the speed of the reaction by moving the control rods up and down. If we move them down, they catch more neutrons. If we move them up, they catch less. So we can speed and slow down the... Now the problem is if things get out, if we lift the control rods up too far too fast, the reaction will quickly get out of control. In the blink of an eye, there will be a huge explosion. That has happened, unfortunately, once or twice. But thankfully, we do this very well, and we use this to make electricity from uranium, from nuclear materials, radioactive materials, making nuclear power. The only downside, really, one of the big downsides, is the fact that the end product, these fuel rods, do get tired after a while because the uranium atoms are decaying. That means there's less and less uranium over time, which means that over time the radioactivity of these fuel rods goes down, and there comes a point when they have to be replaced. And what you've got, though, is you've got a uranium fuel rod that's no good as fuel anymore, but it is still pretty radioactive, and so we've got to look after it somewhere. We've got to stick it in a barrel and decide what to do with it. We've got to look after it for thousands of years. It's going to stay radioactive. Maybe we bury it under the deserts. We've got to make sure that terrorists don't get hold of it. We can't fire it into space, because if the rocket explodes, we'd have loads of uranium scattered all over the earth and that kind of thing. So we've got to be quite careful about what we do with the waste here. So I think what we're looking at here is a very quick summary of nuclear physics. We've got nuclear decay here and its applications in nuclear power, and issues here to do with nuclear waste as well. So that's most of topic 5 in about, hopefully, roughly about 5 minutes, maybe a bit more. Okay, thanks.